Hi everyone, welcome to AI Crack channel. This is Akash Gingwar and today we'll be studying continuity lecture 1 and we'll be talking about basics of continuity and solving few examples. Okay, so let's begin our lecture with the basics of continuity at a point, basically definition of continuity at a point. Right? So we'll start with the same example that we took back in limits, that was fx equals to x square by x. And if you remember that this was divided into two parts, that was x and not defined. This was the case when x equals to 0 and this was the case when x not equals to 0. So when x equals to 0, basically x is in the denominator, that's why function is not defined when x equals to 0. Now if you want to plot this graph, it looked like this one. We had an open circle over here and this was y equals to x, right? This is x-axis, this is y-axis. Now if you remember, we saw that left hand limit was equals to right hand limit equals to 0. Basically, if you're approaching from right hand side and if you're approaching from left hand side, then in that case, we got the limit as 0. But the function was not defined at x equals to 0. Limits were existing, but function was not defined. So if you want to define a continuity at a point, then we say function must be defined at that point, and that should be equals to the value of limits at that particular point. So that basically means LHL equals to RHL equals to f of 0 in this case. Let's say if the point is A, in that case, that would be f of A. Basically, we are considering x approaches A. Okay. So this is the basic condition for function being continuous. Right? And let's say if you want to define the continuity at a point in a crude manner, in a very intuitive manner, then how do we do that? We say if we are drawing a particular graph and we are not lifting our pen, in that case, the function is said to be continuous. Basically, we are not lifting a pen when drawing a particular graph, then the function is said to be continuous. Okay. Let's see certain examples of different types of continuous functions and discontinuous functions. Let's say we have modulus of x. In that case, we can draw the graph without lifting our pen, although there's a bump over here, but we still can say that limits over here are equal, and also we can say that the function value is also same as the limits. That's why the function is continuous, both intuitively and mathematically. Let's say we take one more graph. Let's consider same graph over here with a slight change over here. We have open circle over here and the function value is defined over here. Let's say this is 5. In this case, LHL equals to RHL equals to 0, but function value f of 0 equals to 5. So the function is not continuous. Let's make one more condition over here, or let's take entirely different graph. Let's say the graph looks like this one. Now in this case, even LHL is not equals to RHL because both are not defined. Both are actually infinity. We say that they are not defined, does not exist. So even limits are not defined. So we don't even talk about the definition of function over here, which is ultimately not defined. But with this condition only, we can say that the function is not continuous over here. There can be multiple conditions. Some graphs like this one. Function is defined till here, open circle over here, and we have graph like this one. So over here, limits are not equal. LHL is not equals to RHL. So in such cases also, we can say that the function is not continuous. If you want to talk about certain examples, we can say we have GIF function, we have fractional part function. These are the basic examples of functions not being continuous. Okay. Now let us talk about continuity in the domain, and this is purely for the exam purpose. Some people get a lot of confusion in the languages used in such kind of questions. So let's discuss that in detail, and we'll start with the same example, fx equals to x square by x. Now, if we talk about domain of this function, that would be r minus 0, right? Because function is not defined at x equals to 0, as this is in the denominator. That's why domain comes out to be r minus 0. Now, there can be two cases. They'll ask, discuss the continuity of the function in R. Okay, this is the keyword over here. Discuss the continuity of the function in R. And the second case would be discuss the continuity. That's it. They'll not mention R anywhere in the question or in the language. Okay, so first part was discuss the continuity of the function in R. In that case, we have to consider this point as a discontinuity point because over there function is not defined. So that's why when function is not defined, although limits might be existing, but function is not defined, that's why discontinuous. Okay, this was because we were talking about R, all points. But when we're talking about just discuss the continuity of the function, we will just consider the domain part. So the function is always continuous in its domain. Such functions, not all functions, most of the functions are continuous in their domains. Okay, and we'll always be talking about this. Continuity is always talked in the domain of a function. Okay, when nothing is mentioned, continuity is always talked in the domain of the function. Okay, but when they are specifically giving R, in that case we have to consider this point. So this was just meant for this language difference and nothing else. Now let's talk about point functions. So this also confuses a lot of people, that how can we define point functions and how are they continuous. So let's take multiple examples to prove this point. Okay, let's first understand this constant function. Okay, so we have this value as, let's say, 1, and this value as, let's say, 2, and this particular point is, let's say, 3. Okay, so value of this function is 3, and the function is defined from 1 to 2. 1 to 2 is the domain, and range is just 3. Okay, so this is how the function is being defined. Now you can simply say that this function is continuous based on intuition or based on mathematical logic. You can simply say that limits are existing at all points and function value is also same at all points. That's why the function is continuous. Okay, both intuitively and mathematically you can prove it. The function is continuous, right? There is no doubt in that. Now if we talk about just this end point over here, in this case, can we define left hand limit over here? Can we define? We cannot define, right? Because the function is not defined over there. How can you define left hand limit over there? We cannot even define left hand limit for this kind of functions. But we still say that the function is continuous, right? Because right hand limit is existing and function value is existing. So when we say LHL equals to RHL equals to f of a, when we say that, this means that these two limits, left hand limits and right hand limits, are in the domain. We are considering these only in case of they are existing in domain. Okay, we're not considering them when they are not in domain. So in this case, left hand limit is not in domain, right? Because the function is defined from 1 to 2 only. There is nothing beyond 1 on the left hand side. So that's why in this case, left hand limit won't be defined. So in such cases, we can simply define RHL and f of a, and if they both are equal, then we can say function is continuous. Now let's talk about point function. Now in case of point function, it is defined just at a point. Let's say this is x equals to 1 and this value is, let's say, y equals to 2. So this function has just one value at one point. It's not defined at x equals to 2. It's not defined. It's not defined. Not defined at x equals to 0. It's not defined. Okay, so it's just defined at x equals to 1. So is there any point of discussing LHL and RHL? There is no point in discussing LHL and RHL. If the function is defined at a point, we can simply say that a function is continuous. That was the mathematical logic behind that. Now, if we talk about intuitively, there are two ways to understand this. What we are doing, we are reducing, we are shrinking this constant function to a particular point. That's why this function is also continuous, because it's a part of a constant function. It's a special part of constant function. Constant function is defined for a particular range, but what we're doing, we are shrinking that range to a singular point, and that is what is a constant point function is. Okay, so that's why it has to be continuous. That was one intuitive logic. The other one is when we say we don't lift our pen when drawing a particular graph, right? Over here also we are just drawing a particular point and we are not lifting our pen while drawing the point. So that's why it's also continuous based on intuitive logic. I hope that clarifies everything about the point functions. Now let's talk about inverse of continuous functions. Now we'll talk about these functions in detail when we discuss detailed version of inverse function, but let's just understand what do we mean by this. Okay, let's take an example of log function, or you can say exponential function. So this is our e raised power x function, right? This is our simple e raised power x function. Now when we say inverse of a function, we talk about the mirror image about this y equals to x line. Okay, when we talk about inverse of a function, we talk about mirror image of that function about y equals to x line. So that would be this kind of graph. And if you find out the inverse of this function, you will see that this is y equals to ln x. Okay, so these two are inverse functions and also mirror images about y equals to x. So it's the property says that inverse functions of the inverse of discontinuous functions are also discontinuous and same with continuous. So if the function is continuous over here, it would be continuous over here as well as an inverse, and same with the discontinuity. If we have a discontinuity point over here, let's say function is not defined over here, that same point would not be defined over here as a mirror image. Okay, so both discontinuous and continuous functions are mirror images about y equals to x, and they're also having same kind of properties. Now enough with the theories, let's solve this example. Fx equals to e raised power x minus 1 whole cube cosec ax divided by ln of 1 plus x square when x not equals to 0 and b when x equals to 0, and the function is continuous and we have to find the value of b. So the concept is very easy, that is limit equals to function value at 0, right? That is how we define continuity at a point. So let's find out the limit of this function. So we have limit x approaches 0 e raised power x minus 1 whole cube. I'll write cosec as sine of ax multiplied by ln of 1 plus x square. Now I can see that these all are e raised power x minus 1 sine ax ln of 1 plus x square. These all are actually the penultimate version of their standard format, right? So let's convert them into their standard format. So we have limit x approaches 0 for e raised power x minus 1 whole cube. We'll be writing e raised power x minus 1 whole cube and multiplying divided by x cube. Okay, right? Now we have sine ax over here. So what we'll be doing? Again multiplying and dividing by ax over here. Okay, and for ln of 1 plus x square, we'll be doing ln of 1 plus x square multiplying and dividing by x square. Okay, now this is a stand limit, this is a stand limit, and this is a stand limit. So this x square and this x cube gets cancelled out, we are left with a over here. Now this is 1, this first limit is 1, this second limit is 1, and this third limit is also 1. So what we are getting over here, we're getting 1 by a as the answer. So b equals to 1 by a, and in that case the function would be continuous. Okay, ultimately continuity equations are nothing but one step after limits. Eventually you have to calculate limits only. Okay, now let's move forward with one more example. Let fx equals to ln of 1 plus x raised power 1 plus x minus x divided by x square. Then find the value of f0 so that the function f is continuous at x equals to 0. As of now, if we consider just this function, this is not defined at x equals to 0. Why? Because we have x in the denominator. So this function is not defined. Actually, this function is not defined at x equals to 0. But the question is saying we have to define the value of f0 so that function becomes continuous. It's pretty obvious, right? It's same as this example, fx equals to x square by x, right? And this function was actually x when x not equals to 0 and not defined when x equals to 0. Let's say I define this function in a different manner. I say x when x not equals to 0 and 0 when x equals to 0. I define this function as this one. Okay, what I've done is I have changed the definition of this function to this one, of this function to this one, and now it becomes continuous because we have defined at 0. Earlier it was not defined because of this, but now we have defined at 0, so that's why the function becomes continuous. Okay, so we have to do the same over here, and to make it continuous the value should match with the limits, right? So ultimately we have to find out the limits of this function. Okay, as simple as that. Now we have function as limit x approaches 0. We have limit as, sorry, not function. Limit x approaches 0 ln of 1 plus x raised power 1 plus x minus x divided by x square. Okay, so using the property of log, what we can do, we can write this as 1 plus x times ln of 1 plus x minus x divided by x square. Okay, so let's use the expansion series to find out the limit of this function. So we have limit x approaches 0, 1 plus x times x minus x square by 2 plus x cube by 3 till the end minus x whole divided by x square, right? Let's expand this. We'll be getting limit x approaches 0, x minus x square by 2 plus x cube by 3 and so on, plus x times x minus x square by 2 plus x cube by 3 and so on minus x whole divided by x square. Now that we have x square in the denominator, we should have terms of power 2 or higher in the numerator. So we can see that x is getting cancelled out, this one and this one, right? We have x square by 2 over here, minus x square by 2 basically, and x dot x, that is x square over here. All the other terms are actually higher degree terms. So we are getting limit x approaches 0 minus x square by 2 plus x square plus terms of higher degree whole divided by x square. Now even if I divide by x square, we'll be getting terms of x over here, and since x is approaching 0, so those terms will be neglected, right? So eventually we'll be getting limit as half. So f of 0 equals to half, right? So we can say that if f of 0 would take the value as half, this function would become continuous. Now let's talk about continuity in open and closed intervals. So we have open intervals like this one and closed intervals like this one. So we have 1 to 5 over here and 1 to 5 over here. These are open, these are closed. Okay. Now when discussing continuity in this open interval, we are not going to consider these endpoints. Why? Because these are not in the domain, right? So there is no point in discussing continuity at these points. So this is like this. This is 1 and this is 5. Open circles over here. Now for all the inside points, all the points between 1 and 5, we are going to calculate LHL and RHL both. Okay, we are always going to calculate LHL and RHL both, right? Because for any point, no matter how extreme we go, we can also find one more point over here. For this point also we can find one more point over here because this is open circle. No matter if we find out a point 1.000001, we can still find out a point on the left hand side of this point that would be 1.00000001, right? So no matter what kind of point we are taking between these 2 points, we are always going to find LHL and RHL. Okay, now in this case, when we are considering these endpoints, okay, this is the closed or filled circle over here. When we are considering this endpoint, there is nothing beyond this one because function is non-defined over here on the left hand side, and for this point there is nothing beyond here. There is no function defined on the right hand side, right? So when we are calculating limits for these endpoints, for this particular case we are not going to consider LHL. For this particular case we are not going to consider RHL because function is not even defined over there, right? So as we discussed earlier, in the case of point function, we are not going to consider limits on this side and on this side. For all the points in between, we are going to consider LHL and RHL both. But for the end points, we have to take one-sided limit. Okay. And now that would lead to the discussion of left and right continuous. Right? What do we mean by that? Let's say we have a function like this one. So these are the endpoints, and the function is defined like this one. Endpoints. This is, let's say, 105. Okay. Now, at this particular point, LHL is not defined, right? Only right hand limit is defined. So that's why this is called as right continuous. And for this point, RHL is not defined. Okay, over here LHL is not defined. Over here RHL is not defined. So that's why this function is called as left continuous. Okay. So based on the previous concepts, we can define left and right continuous. At all the other points, the function is a normal continuous function. But at the end points over here, this is right continuous, and over here this is left continuous. Okay, so this lecture was till here only, and in the next lecture we'll be talking about different types of discontinuities. So let's meet in the next lecture. Thanks for watching.